This is the first video in a course on linear algebra that I'm making, designed for any student with a basic understanding of high school algebra, especially those students who want to understand the latest state-of-the-art algorithms in deep learning and artificial intelligence. My name is Jake, and I'm a mathematician who recently got interested in this stuff, especially the artificial intelligence. I also believe in teaching by example, so let's dive right into some problem solving. This is what every video is going to be like going forward. The way this will work is I'm going to state a few examples and solve them with you, and I'll leave you with some unsolved problems at the end, which I'll either solve in future videos or I'll let you guys hash out in the comments. I'm sure you're going to find a nice community of people. Learning any technical discipline by yourself is not as good as learning it in a group. With all that being said, let's solve this problem. Let's begin with this simple vector u equals 4, 1. So we're going to visualize it in the xy plane. We visualize a vector using its coordinates much the same way that we visualize a point. We first find a location, which is x units along the x-axis, so 1, 2, 3, 4, and then 1 unit along the y-axis, 1. The only difference is, instead of calling this the point, 4, 1, we're using angle brackets, which indicates that we should visualize this as an arrow instead. So this is the visualization of the vector u. On the other hand, to visualize the vector v, which is -1, 2, 5, we need to think of these three coordinates as representing the x, y, and z coordinates of a vector in three-dimensional space. So now we visualize an x-axis coming somewhat out of the screen, a y-axis going somewhat into the screen, and a z-axis going vertical. Now we imagine walking -1 unit in the x direction. That means we walk 1 tick mark away from the positive x-axis. Then we're going to walk 2 units along the positive y-axis, 1, 2. And finally we're going to walk 5 units up along the z-axis, 1, 2, 3, 4, 5. And there's our vector v. Since it's hard to visualize a three-dimensional vector on a two-dimensional screen, let me put some things here that'll help. You can imagine that we walked 1 unit along the negative x-axis, we walked 2 units along the y-axis, and finally we walked 5 units along the z-axis. So you can imagine a rectangle whose edges along the x-axis, y-axis, and z-axis are given by -1, 2, and 5. And then v is the vector that goes across the two diagonals of that rectangle, starting at the origin and ultimately making it to the opposite side. In much the same way that over here, u was found by walking 4 units along the x-axis and 1 unit along the y-axis. Now let's talk for a moment about what 2u means. 2u refers to the vector u, which has then been stretched to be twice its length. To compute 2u, the procedure is quite straightforward. Just take the number 2 and multiply each component of u by that number 2. So 2 times 4 is 8, and 2 times 1 is 2. So these are the components of 2u. Sometimes we'll also write this in column form, putting the components into a column like this, 8, 2. Sometimes computations look a little bit nicer in column form. Let me show you. If we had done this computation in column form, it would have looked like 2 times the vector 4, 1, and then it's more easy to visualize the 2 multiplying each number, so we get 8, 2. This procedure of taking a vector and multiplying it by a number, like 2, is called scaling. We say that we scaled u by a factor of 2. Scaling a vector by a negative number works the same way. To compute -v, we think of this as -1 times v, and it means that we keep the same size of the vector 1, but we reverse its direction. So -v looks like this, and its components are found by multiplying by -1 the old components of v. So we get 1, -2, -5. Sure enough, you can check that this purple vector is precisely the vector you would get if you walk 1 unit along the x-axis, -2 units along the y-axis, and then -5 units along the z-axis. But when you're doing linear algebra, it's important to never get too bogged down in the computational details. The most important thing for you to know is that if you multiply a vector by a scalar like 2, that means you're taking that vector and multiplying its length to get a longer vector. Or, when you multiply a vector by a negative number, like -1, you're reversing its direction. in addition to scaling it. Notice that multiplying a vector by the number 1 doesn't change it at all, which is exactly what you expect. It's also possible to add vectors. Let's visualize and compute this sum. Adding vectors works the way you might expect. To calculate u plus v, you simply write them out component-wise. So u is the vector 1, 3, and v is the vector 4, negative 1, and you just add up their components. 1 plus 4 is 5, 3 plus negative 1 is 2. But once again, I think the visualization is much more interesting than the computation. If we visualize the vector u, 1, 3, it's about here, and then we can visualize the vector v, which is 4, negative 1, right about here. Well, now the vector u plus b can be found in the following picture. First, we imagine a parallelogram drawn so that the vectors u and v are two of its sides. Then the vector u plus v is found by just connecting the origin to the far corner of that parallelogram. Another way that people sometimes visualize this is they imagine the vector u, and then they take the vector v, and they move it so that its tail sits at the head of u. And then u plus v is the vector that goes from the tail of u to the tip of v. And sure enough, this vector is 5, 2. It's also possible to combine the operations of vector addition and scaling. The computation is simple enough. U plus 2v, well, we know that u is negative 2, 3, 1, and we're adding 2 times the vector v, which is 1, negative 1, 0. Scalar multiplication means that we multiply each component by 2, so we have 2, negative 2, 0. Then we add the components. Negative 2 plus 2 is 0. 3 and negative 2 is 1. 1 plus 0 is 1. So let's see what this looks like visually. So with the help of my computer to give me a better graphic, where this is the x-axis, this is the y-axis, and this is the z-axis. This is the vector u, this is the vector v, and if we take u plus 2v, we get the resultance vector u plus 2v, which I've visualized by moving the vector 2v so that its tail is at the tip of u. This software that I used here is called Mathematica. As a final problem to get you thinking about vectors in this first video, let's consider the problem of finding real numbers, or scalars, that we can use to scale the vectors u and v, so that when we add these scalar multiples of u and v together, they make the vector 4, 7. So let's imagine u is this vector 3, 3, and v is this vector 2, negative 1. Our goal is to find numbers x and y such that if we scale u and v by those numbers and add them together, we arrive at the vector 4, 7, which is about here. By the way, I'm going to give this vector a name. Let's call it b. Well, just eyeballing this problem, it seems that if we scale up u by a factor of maybe somewhere around 2, and then maybe if we subtract some multiple of v, this is somewhere close to maybe negative 1 or negative 1.5v, it looks like we get pretty close to the vector b that we're going for. So it looks like maybe the values of x and y are somewhere around 2 and negative 1.5. Let's see if we can find them exactly. Writing out this equation, it's x times the vector u, which is 3, 3, plus y times the vector v, which is 2, negative 1, is equal to the vector b, which is 4, 7. What it means to multiply by a scalar like x is that you multiply each component by x. So this is 3x, 3x, and this vector here is 2y, negative y. And that's equal to 4, 7. Then the way we add vectors is we add their components. So 3x plus 2y and 3x minus y are the components. And this is to equal 4, 7. Well, a convenient thing about vectors is if you have an equation involving vectors, then that means you have a system of equations in their components. So the only way for this to be true is if 3x plus 2y equals 4 and 3x minus y equals 7. So this is a system of equations, which we can quickly solve for x and y. Let's do that real quick together. I'm going to multiply the second equation by -1 so that I can eliminate the x's. So this is -3x plus y equals -7. Then I can add these two equations. The 3x plus -3x cancels, leaving me with 2y plus y equals 3y. And on the right-hand side, I simply have -3. Therefore, y equals -1. And then I can substitute that value back in, say, here, giving me -3x plus -1 equals -7. Adding 1 to both sides, -3x equals -6, so x equals 2. So the only solution to this problem is x equals 2 and y equals -1. So we were pretty close here. This value turned out to just be -1. Now I'm going to leave you with some problems to try on your own. But before I do that, I just want to call your attention to what an important problem this is. This is really the basis for linear algebra. Finding ways to express one vector, such as b equals 4, 7, as a linear combination of u and v. Expressing one vector as a linear combination of other vectors is a fundamental problem in linear algebra. As we just saw, it's equivalent to solving a system of linear equations. And with that, I'm going to leave you with a set of exercises.